All right, so we're going to look at proof by cases. So this is a proof method where we're going to basically have to break it down into different cases, meaning if we don't clarify whether or not an integer has to be even or odd or positive or negative, then we want to look at however many cases we have there to try to make it as clear as possible. And remember, we can't leave any ambiguity whatsoever. So we'll start with the result. Which is our claim. And we're going to claim that if n is an integer, then n squared minus n is an even integer. Okay, so what we're assuming here, the if statement, is just that n is an integer. We don't say that it's even, we don't say that it's odd. So we know that there are two possibilities here. So for our proof, our case 1 is going to be n is even. So we'll start by assuming n is an even integer. And that means that we can write n as 2 times k for some integer k. So if we look at n squared minus n, that's going to be the same thing as 2k squared minus 2k. So we get 4k squared minus 2k, and we know that we can factor out a 2 there, and then we have 2k squared minus 1. So this thing, remember, by closure, is an integer, and so we can say this is equal to 2l. Therefore, n squared minus n is even. And I should say right here where l is an integer, just so that we're clear. But we're not done the proof yet. Now we're going to go to case 2. So case 2, n is odd. So for the proof, we're going to assume n is an odd integer. And that tells us that n is equal to 2 times, and what I'm going to do here is say maybe r plus 1 for some integer r. So if I said n was equal to 2k plus 1, then that would mean that it was that and 2k are consecutive integers. So since it's the same proof, I just want to be very clear that this odd integer has nothing to do with this even integer. So we'll look at n squared minus n, and that's going to be 2r plus 1 squared minus 2r plus 1. So if we expand this thing, we're going to have 4r squared plus 4r plus 1 minus 2r minus 1. So those ones will cancel, and what we're left with is 4r squared plus 4r minus 2r. So what's that going to be? 4r squared plus 2r. And obviously we could factor out a 2 here, and then we have 2r squared plus 1. And again, by closure, this thing is an integer. We could call it p. So this is equal to 2p for some integer p that's equal to 2r squared plus 1. So there we have n squared minus n is even. And that means that we've proved the statement, so we'll put our tombstone right here. That's probably the easiest, one of the easiest scenarios that we see by cases. And they're not always this short or obvious, but nevertheless, it's usually not too bad. All right, so we're going to talk about parity now. So parity is whether or not we have an even or odd integer. So if we say that two integers are of the same parity, that means that they're both even or they're both odd, or we could have opposite parity, one even, one odd. So we'll say that we have a claim here, same as the result, remember. Once we prove it, it'll be a theorem. So we're going to let x and y be integers. Then 3x plus 5y is even if and only if x and y are of the same parity. All right, so a proof sketch here. We don't have too many options in too many cases as to what's going on. How many different ways can we have two integers of the same parity? Well, we can have x and y both be even, or we could have x and y both be odd. So those are going to be the two cases that we look at. And remember, if we have x to be 2 times n, then we can't have 2 times n for y as well. It's got to be a different integer there. So let's go ahead and try this. So we have two things that we're doing. Remember, we have an if and only if statement, biconditional. So we have to go the forward direction, and then we also have to go the backward direction. All right, so let's do the forward direction first. That means that if 3x plus 5y is even, then x and y are of the same parity. In fact, that looks a little bit harder, doesn't it? Why don't we do the backward direction first, which says if x and y are of the same parity, then 3x plus 5y is even. So the reason I just went back on that is because when I take a look at this, remember we ran into issues before when we have 3x plus 5y is even, something that looks like that, because then we have more than one variable. In this case, we would have x, we'd have y, and then we'd have another k. So we're thinking maybe if we can do the backwards direction first, that'll give us a clue as to how to do the opposite direction, the converse. Well, the converse of the converse. So in this case, we're going to assume, for case 1, that x and y are both even. And so what that means is x is equal to 2 times n, y is equal to 2 times m for integers n and m. All right, so 3x plus 5y is going to be 3 times 2n plus 5 times 2m. And that's going to give us 6n plus 10m. We can factor out a 2. So we have 2 times 3n plus 5m. And it looks like we're done here because now we just showed 3x plus 5y is even. And if you like to, just to be sure we actually have an even integer, we could always say this is equal to 2 times s for some integer s. So I didn't do that here just because we already have a ton of variables happening. And we can recognize at this point that 2 times an integer is going to be even if that integer is written out as an expanded form or a sum of a bunch of other integers. All right, so now case 2. So case 2, we're going to assume x and y are both odd. So this tells us that x can be equal to 2a plus 1, y can be equal to 2b plus 1 for integers a and b. So what we have here is 3x plus 5y is the same thing as 3 times 2a plus 1 plus 5 times 2b plus 1. And so we're going to have 6a plus 3 plus 10b plus 5, which is going to be 6a plus 10b plus 8. And we can factor out the 2, and we're done the backward direction at this point. So we'll call this thing right here C. For some integer c. Okay, so we're done the backward direction. Now for the forward direction, remember what the statement is. It's if 3x plus 5y is even, then x and y are of the same parity. So there's so much going on here with cases, and then if we don't want to use a direct proof, we can use something else. That's what's actually going to happen here. So what we want to do is use the contrapositive. So what is the contrapositive of the forward direction? It would be if x and y are not of the same parity. Then 3x plus 5y is not even, so we could say it's odd. We know x and y are not of the same parity, so that means that x could be even and y could be odd. And since these are being multiplied by different integers, what I mean is 3 is multiplying x, 5 is multiplying y. We can't just do one case and say without loss of generality. If it said something like 3x plus 3y, and then we had to do opposite parity, we could just do one case where x is even, y is odd, and then say without loss of generality, it's going to be the same for x odd, y even. But in this case, we can't do that. We're going to have to do this for so we have case 1, and then we have case 2, which would be x is odd and y is even. All right, so we're doing the forward direction, a conditional statement of this biconditional, and we're using a contrapositive to do it, and we have to do two cases for this contrapositive. So case 1, assume that x is even and that y is odd. And that means that x can be written as 2 times u plus, well, 2 times u, and y can be written as 2 times v plus 1 for integers u and v. All right, so 3x plus 5y. Remember, we're trying to show that this thing is odd. So we end up here with 3 times 2u plus 5 times 2v plus 1. And now we get 6u plus 10v plus 5. So it's not the exact form that we need it in. So what we could do is rewrite this as 6u plus 10v plus 4 plus 1. And now from these, we're going to factor out that 2. So we have 2 times 3u plus 5v plus 2. And then we have that odd integer form right there. So this is going to be 2 times some integer, we'll call it capital T, plus 1, where capital T is an integer. So you can notice I can write for some integer t, or where t is an element of the integers. It's the same thing that we're saying. All right, so now case 2. So for case 2, we're going to assume x is odd, y is even. That means that x can be written as 2 times r plus 1, and y can be written as 2 times capital S for integers r and s. So again, I'm just trying to use a bunch of different letters here, the dummy variables, so that nothing gets too confusing when we reuse them. I know it's potentially even more confusing because we're using so many, but I don't want to use something like a here, and then we revert that to the last proof, and then we think that it might be the same integer. So just to be sure. So let's look at 3x plus 5y. So this is going to be 3 times 2r plus 1 plus 5 times 2s. And now we end up with 6r plus 3 plus 10s. And we're going to do the same thing that we did last time. We're going to have 6r plus 10s plus 2 plus 1. So that right here we could factor out a 2. And then we have 3r plus 5s plus 1 plus 1. And now we have this as an integer. We'll call that 2 times capital W, let's go with, where W is an integer. And so therefore, our proof is finished and we can put our tombstone. All right, without loss of generality. So I mentioned this in the last proof. Sometimes we can kind of take a shortcut if a second case that we're doing turns out to be exactly the same as the first, just maybe with x instead of y, or vice versa. So let's look at a claim here. And we're going to say let m and n be integers. And here's our statement. M times n is odd if and only if m and n are both odd. Okay. So it's an if and only if statement. And so the forward direction, we would start with if mn is odd, then m and n are both odd. In our backward direction, we would assume that m and n are both odd and then show that m times n is odd. Let's do the backward direction first, the converse. So what we're trying to prove here is if m and n are both odd, then m times n is odd. So what do we do here? Well, for our proof, we're going to assume that m and n are odd. So that tells us that m is going to be the integer 2k plus 1. N is going to be the integer 2l plus 1 for integers k and l. So now if we multiply those out, m times n is going to be 2k plus 1 times 2l plus 1. And so when we expand this thing, we're going to have 4kl plus 2k plus 2l plus 1. And it's pretty easy to see here. If we take out a 2 from just the first three terms, we're going to have 2kl plus k plus l, and then we have that plus 1 on the outside. This thing right here we could call x, so we have 2x plus 1. So there's our odd integer. So therefore mn is odd. Okay, so now we want to do the converse, the forward direction. So here we're going to prove if mn is odd, then m and n are both odd. And the way that I want to do this is using a contrapositive, because we already did this direction. It seems pretty easy. So the contrapositive is going to say if m and n are not both odd, then m times n is even. So if we think about what that actually means, it means that m is even or n is even. So our reasoning for that, if we negate m and n are odd, we get m or n is even. So basically we have two cases here. The first case is m is even. The second case is n is even. But you can see what happens if we let m to be even. So without loss of generality, we're going to say let m be the even integer. So that means that m is going to be equal to 2 times a for some integer a. Now, if we look at m times n, that's really going to be 2a times n, which we can write as 2 times an. We don't even care about n, what it is, if it's even or odd. So this right here is even. And we're going to be done right here because of the statement without loss of generality. So if we didn't say that, look what would have happened. We would have had to say, well, n is even. And that means that n might be 2 times b, and then we would have m times n is m times 2b, which is 2 times mb. You can see it's going to be basically the same exact proof, and so we don't need this at all. So if we say without loss of generality, let m be even, then that's also covering the case where n is even. We couldn't do that before because we had 3x plus 5y. So if I have this even and this odd, if I say without loss of generality, that means that they could be switched. Well, 3 times even is not going to be the same as 3 times odd. So that case, we can't use without loss of generality. In this case, we can, and we're done our proof.